Okay, well, let's go ahead and begin here. Um, the uh, the big thing to keep on your mind is the project, which is due on Monday, April 20th. So that's coming up. We've talked already before about what's expected for the project. So if you have any questions about that, feel free to get in touch. Um, Today we're going to continue talking about hydraulic jumps, and in two different ways. We're going to talk about hydraulic jumps in terms of their length, and then also hydraulic jumps are often caused by underflow gates. And so when we discuss underflow gates, then we'll also have some hydraulic jump applications there as well. Any questions before we start on today's new material? I guess maybe I'm not sharing the screen yet, right? That's more like it. All right. All right. Any questions? All right. So this is where we left off last time. We were talking about some different ways that you can predict how long a hydraulic jump is. Remember, a hydraulic jump is rapidly varying flow that is caused when supercritical flow has to jump back up to a subcritical depth. And so the upstream and the downstream depths in a hydraulic jump have the same amount of momentum. They certainly don't have the same amount of energy, but through the momentum depth diagram we could graphically solve for what the downstream depth would be, or we can use the Bellinger momentum equation. Here what we're going to do is both. We're going to find the depth after the hydraulic jump and then use that information to predict what the length of the jump is according to three methods. One is with a Bureau of Reclamation nomograph, and so the figure approach where you use the Froude number upstream of the jump to predict the ratio between the length of the jump and the downstream depth. So that'll be the first method that we use to predict the length of the jump. The second method that we'll use is the Hager equation, which predicts the length of the jump as a ratio of the upstream depth. By then we'll know both y1 and y2. And then the third equation, what our book called the another equation, we'll just use an A factor of, let's see what I used in my examples there. So we'll assume that A is equal to 5.5 just for purposes of calculation. The textbook mentions that there's typical values between about 4 and 9 for that. All right, so what you'll need to do is first of all find y2. So find the depth of the hydraulic jump where we know the velocity upstream, the width of the channel, and the depth upstream. And so with the width of the channel and the velocity, you'll be able to find what's the flow rate. And knowing the channel geometry, you can have both T, which is the top width of the channel, and the cross-sectional area. So the area is going to be the depth multiplied by the width of the channel. So from the Froude number, you'll be able to solve the Bellinger momentum equation and find y2 after the jump. And then once we have that jump length, we'll use method 1, method 2, and method 3 to find out the range of the length of the hydraulic jump. So I'll pause for a moment from talking and give you a chance to start your calculations on that. All right, well, let's take a look at where things stand here. First of all, calculating the length of the hydraulic jump. After we've determined the downstream depth. Okay, so the The problem statement told us that the channel's 25 centimeters wide, y1 is 10 centimeters, and the velocity is 5 meters per second. So the area is the width of the channel multiplied by the depth, and then once we have the area of the channel, we can multiply that by the velocity, and that's where the flow rate comes from. And so we're getting this Q by V1 times A1. Okay, and we just want to double check first of all that we have supercritical conditions upstream, because if not, it's not going to be a hydraulic jump. And so calculating the Froude number at that upstream location prior to the jump, you can see with the substitutions that we've calculated that the Froude number is going to be 5.05. So now we put that Froude number and the upstream depth into the Bellinger momentum equation, and this is the equation that we can use in order to calculate the downstream depth after the jump. So it's jumping from 10 centimeters, no, I'm sorry, 10 centimeters was the upstream depth. It's jumping from 10 centimeters all the way up to 2/3 of a meter. So that's a pretty dramatic jump. Its depth is increasing by more than a factor of 6. So we have that y2, and so let's look at from the figure the Froude number of 5 and what it means for the length of the jump and the y2 ratio. So here on this figure, we calculated that the Froude number is 5, and so we start on the figure here and go up to the figure, to the curve, and then over to the left. And so that is about just greater than 6, maybe 6.1. So 6.1 equals the length of the jump divided by y2. And so here, the length of the jump divided by y2 is 6.1, so then that means if we know the y2 depth, which we do because we just calculated it, then we can calculate the length of the jump by multiplying 6.1, which was the y-axis off of that figure, by the known depth after the jump. So it's going to take about 4 meters to go through that transition. So the rollers is going to be less than that, because if we go back to the figure, remember this is talking about the overall length of the jump, not just the length of the rollers, which is where you'd have that visual kind of foamy, white entrained air, really visible part of the jump, but the overall length of the jump where it's still rapidly changing its depth before it reaches equilibrium would be 4.06 meters. Before we move on from this figure method, are there any questions about how we use the Bureau of Reclamation nomograph to calculate what would be the length of the jump? Any questions at all? Okay. So that was the first method for calculating the length of the jump. The other is the Hager equation. So here's the Hager equation. It says that the length of the jump is going to be the upstream depth multiplied by 220 times the hyperbolic tangent multiplied by the Froude number divided by 22. So we previously calculated the Froude number to be 5.05. And so the question is, do you have the hyperbolic tangent function in your calculator? And if I remember correctly, the Casio calculators do. So let me pause for a second and give you a chance to try that. And let's see, according to this Hager method, what would be the length of the jump, and see how closely it compares to the Bureau of Reclamation nomograph approach. Jeffrey's got it. Good job, Jeffrey. 4.96, that's exactly right. And so, I mean, it's in the same ballpark as the Bureau of Reclamation nomograph, but when you have different methods for an empirical estimation, like how long a hydraulic jump is, it's good to calculate it according to all the different methods just to give you, the look at what different models are predicting. And, we're hearing a lot about models in the news these days because there's different models that are predicting the number of people who will be infected with the pandemic, the number of people who will die, and different models have different assumptions, and it's good to look at a wide range of estimates just to maybe give you an idea of the bounds. So far it's pretty tight though. If we use the third method for this estimation, where we're assuming A equals 5.5, this is the simplest of them all. So simple our book didn't even give this one a name. It just said another method for predicting the length of a hydraulic jump. So 5.5 multiplied by the difference in depths. And so that one would predict that we have a length of the jump of 3.1 meters. So that's kind of a spectrum of the estimates from about 3 meters up to possibly as much as 5 meters, with our midpoint value being approximately 4 meters of length. Now these can be physically measured out in the field, but the reason why we would want to predict the location of the jump and its length is that sometimes you have a hydraulic jump setting up after the spillway on a dam, and there could be a whole range of different flow rates going over that spillway. One day maybe it's a really high flow rate, other days it may be a lower flow rate, and so the size of the jump and its location and its length could change over time. We don't always have steady flow conditions. They can be unsteady and variable over time, and so we have to be able to predict these things outside of just observing them directly. All right, so what we're going to talk about now is which method is best. I guess if one method was best, we would just only use that method. The methods are different. And so I guess this method is definitely not best. Why is this not the best? Is because we don't have any information on what value to use for A. Our textbook just gave us a range of empirical values, and so I tell you, I don't know which one is best, but I do know which one isn't best. Whether to use Bureau of Reclamation or the Hager method, use them both, just to give you an idea. So let's talk about underflow gates now. And underflow gates are one of the things that can cause a hydraulic jump. The simplest kind of an underflow gate, which is pictured here on the screen, is often used in agricultural irrigation, where you have water coming from one canal into a field, for example, to irrigate a crop. You can regulate the flow just simply by how open the gate is. And the handle at the top could just be as simple as a piece of rebar that's been welded onto a plate. And so this is the sort of control that is pretty crude but also low cost. At the upper end of the spectrum, one of the first projects that I was involved in as a practicing engineer before I went back and started to work on my PhD, I was designing an irrigation diversion using really big, heavy gates like the one that's pictured here on the left. And the gates, each one of the metal pieces weighed several hundred pounds, and so you couldn't just lift it up with, by hand. There were hand crank that gave you a little bit of mechanical advantage, but then most of the time they'd mount a motor on the top there so that they could be controlled remotely. But both of these are examples of underflow gates that are used in irrigation. The picture on the right is showing how gates could be used in water treatment and wastewater treatment processes to control the amount of water that's getting into, for example, a flow equalization basin. Here's a photo that's taken from the Netherlands. They have a lot of canal systems throughout the Netherlands because it's a very wet country, and more than a third of the land area has been reclaimed from low-lying areas that would normally be inundated by seawater. So water resources is really important there, And this is a gate that can be raised and lowered, and you can see that it has a radial shape to it. And so to predict the flow rate that's going under a gate, we have to apply the energy equation. And what we look at in gate analysis is the upflow conditions and relate them to the conditions after the flow has gone through a period of contraction. And so if we look at the variables here, in the figure, what they're calling y sub g is the depth that the gate is open. So that's how far off the bottom of the channel the gate's been opened. And what you'll notice is that the water continues decreasing its elevation a little bit. And that's a similar effect to what you observed in the fluid mechanics lab when we had the orifice equation. You may remember that we had an orifice lab where there was a contraction after the water exited the tank, where the diameter continued to decrease a little bit because the water was still accelerating. It doesn't stop accelerating just immediately after it gets out from either the orifice in a tank or out from under the gate. Now, there are some similarities here actually to the orifice equation, and we'll see those similarities with some of the future equations that we're looking at. But if you think about what's driving the flow of water under this gate, it's because the water is pressurized due to this great depth y1 upstream of the gate. And so if we assume that there's no energy loss between the upstream and the downstream location, then we could use this equation saying that the energy in the form of the depth and the velocity head upstream is equal to the depth and velocity head downstream. It's just that there's an exchange between those forms of energy, an exchange from the depth adding additional velocity downstream. Most of these gates are rectangular in shape, and so remember that the flow per unit width, if we take big Q and divide it by the width of the channel, then we assign that variable lowercase q. And so the lowercase q, the flow per unit width, can be found by looking at the relationship between the upstream and the downstream depths. There usually is energy loss though. This equation that I was showing on screen initially is assuming that there's no energy loss. But in reality there is, and so the energy equations I'll show you from here on out makes use of energy loss that's in part related to the coefficient of contraction. So C sub C here is showing the contracted depth of flow compared to how high the gate is opened. And so if the gate is opened about 1 meter, then you'd expect the downstream depth Y2 to be between 0.59 and 0.62 meters. And a good part of the energy loss is in some ways related to the contraction that occurs and turbulence upstream of the gate, a little bit of interaction with the bottom of the channel downstream of the gate. So we have a flat underflow gate and a radial underflow gate, and the hydraulic situation is very similar regardless of that shape. Here, instead of the y sub g that we saw as how high the gate is opened, some texts just refer to that variable as w. And so be aware that here, when we talk about the height that the gate is open, it contracts down to y2. And so the downstream depth would be the coefficient of contraction multiplied by W, which is how high the gate is opened. Now these gates aren't used to quantify the flow. Their functionality is to regulate the flow. And so it's to control how much water is going through one canal versus another. It's not used in the same way that a weir is utilized. You remember we've talked about a sharp-crested weir and broad-crested weir, and so some of the hydraulic structures that we've discussed previously have existed primarily to quantify the flow, but this is used to control how much water is going where. The nice thing about an underflow gate compared to a weir is that there isn't going to be the accumulation of trash and sediment and debris upstream of the structure. The broad-crested weir and the sharp-crested weir both had the disadvantage that it's basically an obstacle on the bottom of the channel. And so anything that's getting pushed along the bed, like gravel or sediment, anything that would otherwise flow easily underneath our gate would get stuck on a weir. So the advantage of this gate is that it is going to prevent sedimentation. And here's the equation that relates the flow rate under the gate. You notice it's related to the orifice equation, where when we were using the orifice equation last semester in fluid mechanics, we used the square root of 2gh to describe the velocity of flow. And so here, this flow rate equation is saying that it's the width of the channel, B, multiplied by the opening of the gate, W. And so now that's giving us a cross-sectional area. B times W is the area of the opening. And then square root of 2gy1. And so that is where we get the velocity of flow under the gate. And the square root of 2gy1 gives us velocity. So velocity times the area is flow rate. And then finally, we put a discharge coefficient in to account for energy losses. And you can see that the function that I give you for the discharge equation is largely related to the coefficient of contraction. So you calculate a coefficient of discharge with the coefficient of contraction and then the ratio of the depths. And this same equation applies whether you have a radial gate or if the gate itself is flat. Any questions about this equation? Well, I've got a question. My question is, how much flow can we get under this gate? Based on the upstream depth is 2.7 meters, and so we're saying the depth upstream of the gate is 2.7 meters, and the canal is 4.3 meters wide. So that's talking about the width, which is parameter B, and the I just led you astray. The width of the sluice gate is different from the canal width. So actually B is the width of the sluice gate, so that's 1.5 meters. So the sluice gate doesn't need to be as wide as the full channel width. What we're going to do is we're going to open up that gate 45 centimeters, and so W here on the figure is what the equation has as y sub g. So that's how open the gate is. And then after contracting means that after it tapers back down to its minimum depth, it gets to 27.5 centimeters. So you're going to be able to calculate the coefficient of contraction because we know how much the gate is opened. That's 45 centimeters. And then the after contraction, the Y2 depth is 27.5 centimeters. So C sub C is Y2 divided by W. So we want to know what's the flow rate. So the steps that you're going to have to go through is, first of all, let's calculate the coefficient of discharge based on the coefficient of contraction and the depths. And then after you have the C sub D, from there it's just plugging in the upstream depth, plugging in the gate height and the width of the gate, not the width of the channel. Let me pause for a moment and give you a chance to plug those numbers in, and then we'll look at the solution together. Okay, so the first thing that we've got up on the screen here is the sketch with the variables assigned to the depths that are known. So the upstream depth is 2.7 meters. The gate is opened 0.45 meters up off the bottom of the channel. After contraction, the depth goes down to 0.275 meters, and so that's Y2. So the coefficient of contraction is 0.6111. And if you put that coefficient of contraction into our formula for the coefficient of discharge, along with the upstream and the downstream depths, then we get the discharge coefficient is 0.5822. So we're going to use that to calculate the flow rate based on the, essentially what's the orifice equation, the square root of 2gh. Everybody with me so far? Any questions on this quite yet? Okay. So now if we substitute that discharge coefficient that we've just calculated and the width of the gate, not the width of the channel, I gave you both maybe just as a trick. The height of the gate opening, so the gate is opened 0.45 meters up off the bottom, and then square root of 2gh, where really what we have inside that square root is the depth of the flow upstream of the gate, so that's what's causing the velocity. So we should expect to have a flow rate of 2.86 cubic meters per second. So a gate like this exists to give you the control over how much flow is going, for instance, into an irrigation canal. And so we could use this relationship to tell us if we know what flow rate we're trying to get, like if that's too much water, if we only needed 2 cubic meters per second to go into the canal, then we would close the gate down a little bit. So we would change W, and then that would reduce the flow rate if W was less. Any questions on this example? One thing I'll mention right now, just because I'm thinking about it, is it's not always the case when these gates are used that all of the water that's upstream of the gate is going under the gate. So it could be that you're opening up this gate from like a lake, or maybe it's from a river, and so there's lots of different gates along the river. Maybe you have hundreds of farms along a river, and any one individual farmer isn't going to be diverting the entire river by opening up their gate. And so I wanted to just mention that this water level, Y1, isn't always going to change based on how much you open the gate. Sometimes it will. You know, if all of the flow from the channel has to go under the gate, then changing W is also going to change Y1. But it isn't always the case that how much you open the gate changes the flow depth. You know, if you're taking water from a lake, for instance, then the lake is so enormous that you're not going to have any effect on the water level in the lake by how wide you've opened the gate. So this is showing the underflow gate along with the hydraulic jump that forms after it. And how much you open the gate is going to control where the hydraulic jump sets up. And we talked last time about kind of the perfect condition. Ideally, what happens is that the gate would be opened an amount that has the hydraulic jump match up with the normal depth downstream. And so that's one way to prevent the hydraulic jump from drowning, is just to make sure that the gate isn't opened too much. Because the more you open that gate, it's going to reduce the depth of the downstream hydraulic jump and bring the jump closer to the gate. There's a process we can go through to make sure that the jump isn't drowned. The first being that you'd calculate the normal depth of the channel, and then you'd find out what is the critical depth for the flow rate in question, just to make sure that you have supercritical conditions upstream of the hydraulic jump. And then sometimes problems like this will ask you to find the maximum gate opening. You know, how high can you open the gate to prevent the drowning? Well, that is solved by making sure that the gate doesn't exceed the height of Y1 divided by the coefficient of contraction, that produces the normal depth downstream. So this is kind of convoluted. It's a multi-step process, but what I'll say is, the channel downstream, based on the roughness and the slope and the width of the channel, use Manning's equation to find out what is Y2. So Y2 just means the normal depth in the tailwater. Now set that equal to the depth after the jump, and then you'd find out what's the upstream depth, so the sequent to that. So Y1 means the supercritical that has the same amount of momentum function as the downstream depth. And so then how high you can open that gate, it shouldn't be opened more than the coefficient of contraction being the denominator. So Y1 minus the coefficient of contraction will tell you how much you can open up the gate. So you'd use the, in this case, the Bellinger momentum equation here is solving for the depth upstream. And previously, I've shown you the version of the Bellinger momentum equation that's solving for Y2. And so this is rearranging the equation for Y1 rather than Y2. And the textbook gives you both forms of that equation, but this is solving for the upstream depth rather than the downstream depth, because in a question like this, like how much can the gate be opened, the starting point isn't the known is not the upstream depth. The known is the downstream depth that you would get from Manning's equation. And so if the gate is not that, if it's not open more than that, like if W is relatively small, then that pushes the hydraulic jump further away from the gate. But the more you open the gate, the closer the hydraulic jump will get to drowning. So the ideal case that we talked about is that the depth after the jump is the normal depth. Okay, so let's look at this second example, and this takes us through that process that I was just explaining. You'll notice that we have a complex system here. We have this depth after the jump, the depth before the jump, and so Y before and Y after is defined by the Bellinger momentum equation. Then there's the underflow gate component of it here, which is described by the coefficient of contraction, and then this orifice equation, which is also taking the discharge equation into account. I've given you the parameters that you'd need for Manning's equation to find out the depth, the normal depth. So this is a rectangular channel that is 5 meters wide. And so the first thing that you need to do, according to that step-by-step process that I show you here on this slide, step 1, calculate the normal depth. So find the normal depth using the slope of 0.003, an n value of 0.02, and the Q of 25 cubic meters per second. So I'll find Manning's equation and paste it up there in case you don't have it in your memory. Just 1 second. Okay, so step 1 is find the normal depth. So with this slope, with this n value, with this given flow rate, and the fact that we have a width of 5 meters, then what will be the depth of flow? And we're going to say when you find that depth, set it equal to the Y after the jump, and then you use the Bellinger momentum equation here to find out the depth before the jump. Let me paste that off to the side so you can see that. So you'd use this formula to find Y before the jump, and then the coefficient of contraction will tell us what is the W depth, and then finally we can find the depth behind the gate because we know the Q, the coefficient of discharge, the width of the canal, and the gate opening. We know how much the gate has been opened, and so then the only unknown would be Y1. So those are the steps. Let me pause for a moment and give you a chance to do those calculations. Okay, let me show you the workflow for this, how we could find out how much the gate can be opened, and then what's the depth of flow behind the gate for the situation that's described. The steps as I've outlined it is, first we're going to calculate the normal depth using Manning's equation, and the normal depth is describing this parameter, the depth after the jump. And then we'll get the depth before the jump using the Bellinger momentum equation. Then we're going to find out the depth underneath, how high the gate is opened with the coefficient of contraction, and then finally the relationship that describes the flow rate and the depth of flow upstream of the gate is this flow rate equation. So here are the calculations for this. What we have is the normal depth calculated with the Manning's equation. So I substitute in the flow rate that's known, substitute in the n value of 0.02. The area is just going to be 5 times the depth. The wetted perimeter is 5 plus 2 times the depth because it's rectangular. The wetted perimeter is the bottom width and 2 times the sides, which is the normal depth. And then you can see that the slope is also in there. If we put it into the solver, then what we find out for the normal depth is 1.76 meters. And so we're saying that the flow after the jump is 1.76 meters. And so if that's 1.76, then what is the flow rate before the jump? And so to do that, we have to know the critical depth, because the momentum equation is having the ratio of the critical depth to the depth downstream. So you see that I found the flow per unit width of 5 meters squared per second, and from that you get the critical depth of 1.366 meters. And downstream of the gate, the conditions are subcritical, so it is going to jump up through a hydraulic jump. And now the maximum gate opening, we use the momentum the Bellinger momentum equation, which solves for the relationship between upstream and downstream in a hydraulic jump. So that tells us before it jumps, the depth would be 1.022 meters. And so then the gate can be opened 1.703 meters because of the coefficient of contraction. And then finally the depth behind the gate, if we use the gate flow equation, the only unknown here is going to be Y1, because we have every other parameter like the flow rate, the coefficient of contraction, the Y2 depth. And so Y1 is the only unknown, and again you'll have to use solver because we've got Y1 in the coefficient of discharge and also here in the velocity term. So Y1 exists in more than one spot, so that's why we use the solver, and upstream of the gate the depth should be 1.883 meters. I apologize I've kept you a little bit late. I guess the only consolation is that I know you don't have to walk very far to get to your next class. You probably just stay seated in the same spot. That's a lot. We will be able to spend a little bit more time talking about gates in our class on Friday. Let me just go back to the announcements before we go our separate ways, and the reminder being that your final project report is due on Monday. If you have any questions as you're working on it, get in touch and I will be glad to meet with you or answer any questions via email. That's it for today. Sorry we're late. I'll give you back your 2 minutes on Friday. Hope you're doing well. See you later. Bye.